Okay, welcome back to CS 2040S for the last time. I hope everyone has had a great semester, and we have one whole class left today. So what are we going to do today? Well, I thought maybe what we should do is just try to cover all of quantum algorithms in one lecture, right? Good plan? Okay, okay, maybe we won't do that. Maybe that's not the plan. So what we're going to do today is just a sort of quick review of some things, some administrative stuff, and some wrap up. Okay, so that's the plan for today. Before I get started, I just want to personally thank all the tutors for their hard work. So I think from what I can tell, they have done an excellent job this semester. And I hope you have appreciated the work they've put in. They have been super busy, and despite that, they've taken time out of their very, very busy schedules to help make this the excellent class it is. We could not run this class the way we do without the excellent tutor team we have. So I would like to thank the tutors, and I would encourage you to thank your tutor as well. Okay, so what are we going to do today? So in part, as I said, I want to do a little wrap up and a little bit talking about what comes next. Okay, so here's today's plan. I have some announcements. I will talk a little bit about what comes next, and in doing so, we're going to review a little bit of what we've done. I'll give you my favorite top 8 algorithm design tips, and then we'll wrap things up. Okay. Good. So let's begin with some announcements. First of all, as you might have heard, there is going to be a final exam in this class. As far as I can tell, it is on Tuesday, April 26th, but you should double check that date, because if I have that wrong on the slide, that's no excuse. So you should go and double check and make sure that's right. I believe it is at 1 p.m. In the MPSHs. You will need to check the specific hall assignment. Okay. Yeah, the seat allocation should be on EduRec. Okay. What else do we need to say about the final exam? In terms of COVID issues, you should keep track of whatever the current NUS policies are. As far as I currently understand them, and again, please double check, you no longer need to test before coming to the exam. I would still encourage you to test, because I would still prefer not to end up with several hundred sick CS 2040 students a few days after the exam. That would be very unfortunate. So it would still be great if we could maintain some caution, especially if you feel unwell. Please do take a COVID test. If you do test positive, please don't come to take the exam. Other accommodations will be made. Okay, so that's all I wanted to say about that. Is just, again, please follow whatever the university policies are, and please be careful, since none of us want to get sick. Okay, good. What else? People sometimes ask, so what's going to be on the final exam? To which the general answer is everything. Anything we've talked about, anything we've covered, whether in lecture, recitation, tutorial, problem sets, doesn't matter. Everything we've covered is fair game. You can bring a 1-page double-sided cheat sheet full of notes. You can do whatever you like with that cheat sheet. No magnifying glasses, but anything you want, that's fine. Okay. No, you don't need a calculator or a phone, etc. I will post online last year's paper. The year before that was sort of weird, because that was the COVID year and it was done in a strange way. But you can find, you can find all the old papers on the NUS library. But I will post last year's in particular, since I think that is the best model for what this final exam will look like. Okay. Good. The format of the final exam, about 75 to 80% of it is going to be MCQ, basically a lot like the midterm, and about 15 to 20% will be short answer. Okay. And when I say short answer, I do mean short. I do mean keep what you write short. Remember, we're going to have to look at 650 of these. So, keep your answers succinct and direct. Sometimes with short answer questions, I've noticed that students think, if I write more, maybe I'll write whatever the professor is looking for, and so that's going to be better, right? But when I see someone who's written a whole lot of nonsense, what I actually think is, gee, they wrote a lot. They probably don't really understand what they're talking about. There was a one-sentence short answer to the question, and they wrote like 2 pages of text. They probably don't understand what's going on here, okay? So you don't need to write a lot. And the more you write, the more chance that you write something that is false, and writing things that are false, well, causes you to get it wrong, okay? The other thing that I would encourage is to draw pictures to explain what you mean. Okay, try to be neat. If I can't read what you've written, you won't get credit for it. Part of what you're testing on a short answer question is communication. Can you explain what you understand? So if I don't understand your answer, even if you have the right idea, you're not going to get credit for it. So that is just what I want to warn you about. Okay. I see a question in the chat. What if we wrote more because we don't understand the question? Well, try to understand the question. My job is to try to write the questions as clearly as possible, and I do the best I can. And you have to try to understand it. That's the way a test works. Obviously, it is a good idea to state carefully what you are assuming in a question. So for example, if the question doesn't specify if a graph is connected or not, and you say, I'm not going to assume this graph is connected, and give your answer in those terms, then, well, in a lot of cases that will clarify things so you get it right. Obviously, you can't make any assumption you want. If you make an assumption that obviates the question, then it doesn't help. Okay. But in general, if it's a reasonable thing, the question doesn't specify connected or disconnected, either one is a reasonable thing, then either is fine. Good. What else? Okay. Next things next. The grad TAs who have been leading the recitations this semester will be holding review sessions next week. Okay. So there'll be 4 or 5 different sessions that you can optionally attend. Each session will be on one topic from this class. So for example, one of the TAs is going to hold a session on sort of theory and searching and sorting. One's going to hold a session on hash tables, one on graphs, and so on. Okay. And so you can attend whatever you like. Obviously, this is completely optional. The goal of these sessions is just to give you a chance to, ask questions and clarify and review things that you are confused by. Okay. I don't know if they'll be recorded. We'll have to talk to the TAs. One thing we're going to do is, because there might be a lot of people with questions, and because, well, we don't have infinite amounts of time, what I'm going to do is ask you if you have specific questions that you would like addressed during the session to indicate them in advance in a Coursemology survey. Okay, it's not there right now. I'll put it up later today or tomorrow. And you can specify in advance some questions you're interested in. And if the TA notices that a lot of people are confused about one thing, we can make sure to address that. And then beyond those questions, we can deal with things on a first come, first served basis. But that's one way of making sure that we hit the most important topics. Okay. And yeah, so basically submit your questions in advance, show up, talk with the TA about the answers, ask more questions then. There will be the TAs are not preparing a lecture for this. They're not preparing something specific. They're just there. They will just be there to answer questions on a specific topic. Okay. Good. There's a question of what is theory. Theory is all the stuff we talked about in terms of asymptotic notation and recurrences, and sort of all the stuff that does, and all the stuff that doesn't neatly fall into a specific algorithmic category, all the sort of algorithmic stuff. By the way, you can also be fairly loose about these in the sense that you can show up for any session and you can try to ask any question you like if there's free time, but the focus of the session is going to be on the topic specified. But you can try to ask any question you like and see what you get. Okay. I think most of the sessions will be about an hour or so. So there'll be about 5 sessions. Yeah. And yes, I can't, in terms of the clashing, I can do, we can only do the best we can. We've specified 5 sessions in the hopes that that will give people a chance to get to at least some of them. I assume that most people will not want to attend all 5. That sounds like a lot of extra time spent. But of course, up to you. Okay, what else? Teaching feedback. There is a departmental teaching feedback form that you have probably already seen. Okay, and I encourage you to fill in that. That sends feedback to the department and the university as to how things are going, what's going well, what's going badly. The department chair and the dean and so on, they like to get that information. Okay. I would also ask, I'm also going to put up tomorrow a survey in Coursemology with feedback very specific to this course and very specifically to me and the TAs. Okay. So I would ask you, if you can, to please fill that out. And that will sort of help us to improve the class for next year. Okay. Good. Okay. Other thing, sort of last chance for submissions on problem sets and optional problems and so on is Friday night. Okay, that's sort of the cutoff for problem sets. It is important that this doesn't impinge on your reading week. I really don't want this to run into reading week. I also don't want the TAs to have to grade things during reading week. So that's the last deadline for submitting things. And then once all the submissions are done and all the grading is done, that's when we will do the final XP computation. What I notice now, if you look down right now, student number 500 or so is around level 31 with a few thousand XP left to get from the last problem set. So I imagine down to like 500 or so, people should be at level 33, 34, 35. Okay. Good. Problem sets, other thing, I'm going to run a plagiarism check for, one more time. Alas, there have been a few cases this semester and a few suspicious problem sets that I have been tracking for a little bit. I'll be doing one last check. If you're caught, you'll be liable for disciplinary action. If you confess before you're caught, then just a 0 on the problem set and no further consequences. So I don't want to waste time talking about that, but that's just one other thing that's happening. Okay. Good. What else? Overall, this has been a great class. I've really enjoyed working with you all this semester. And in general, people have done really well and seem to really be enjoying this material, which is great. I really like that. One thing that we've noticed as we've gone through things is that a few of you may need to shore up some of the basics, may need to do a little revision of some sort of basic programming skills, basic problem solving skills, and so on. In general, in the bigger picture, sort of being comfortable and experienced with sort of basic programming skills is quite important. So just for example, I told you I was talking to the CS2109S instructor, and he was saying that, an assignment might begin something like, please start out by implementing BFS. And then the actual problem is doing something interesting with that. You have to be able to easily implement something like BFS without a lot of hard work or thought. And so one piece of advice is, if you are struggling with things, this summer is a great time to review. And in fact, there may be a small program this summer that we may contact you about after exams with some suggestions. Okay. I see a question in the chat. Can we access Coursemology after the end of the semester? Yes, I will leave this. I will leave all the material available. And as you know, all the videos are available on YouTube. Okay. What else? It's also a good idea to practice for technical interviews. So start at the end of year 2, it's likely a good idea to think about doing an internship. And that's going to mean going through technical interviews. So this summer is also a good time to begin doing some practicing for technical interviews. And in fact, this summer, we are running a technical interview preparation program. The department is, that is. So it's going to essentially be a 10-week program that gives you a chance to sort of practice technical interview preparation. So it will involve some work on how to prepare a resume, some review of technical interview skills, some work on how to do problem solving, some mock interviews, and so on. So in general, it will be a good way to get ready for technical interviews that you might have to do in the future. This is something available for you to sign up for right now. Okay. Have I opened the survey on Coursemology yet or not? I don't know. I'm checking Coursemology as we speak. It should be opening now or by the end of class. Okay. Let's see. Does that make it open? Is it published now? I don't know. If it's not published yet, I will check. Anyways, so basically every week there'll be a weekly session on Monday, and then you'll do a mock interview, and then you'll be expected to do some coding questions and so on. Okay, it's not intended to interfere with anything else you're doing. If you're doing Orbital or an internship or anything else, it shouldn't get in the way. It's basically intended to be a limited time thing. So yes, this is every week there'll be all of these things happening. Okay, so I'd encourage you to go and sign up for that. This is the first time we're doing this, but I think it should be useful. Or at least that's our hope. And as you see, we have an email address here. You can email and ask about it. Ask any questions you have. Okay, good. What else? Okay, yeah, so that's, I think, it for announcements. Okay, so next things next. Or I guess let me quickly check if there are any random questions in the random questions thing that I should answer before I go on. Where is the Rickroll? See, a Rickroll is most entertaining when it's not expected, right? If you know it's coming, it's no fun at all. Let me see. Any other questions here that I should answer? Will the last 2 tutorial participation be counted in our Coursemology? Yes. All the stuff that's supposed to be counted will be counted. There's a question, can we ask clarifications during the final if we don't understand them? Yes, you can. I'd encourage you not to ask clarifications that are unnecessary. Don't be so paranoid that you try to clarify every sentence, but if something is unclear, then absolutely. Let's see. There's a question of, if we do catch COVID on exam day, are we in trouble? No. If you have COVID on exam day, we will find something to do, depending on, of course, how unwell you are. Obviously, if you are unwell and unable to do things, then you can't take the midterm that day. The final exam that day. If you are well but still testing positive, then perhaps there are some accommodations. This is a departmental policy, and we'll have to consult the department about it. But there'll be ways to make things work. Okay, what is 42? The answer to life, the universe, and everything. What is the mystery function calculating? It's a mystery. Okay, good. Okay, good. So onwards, the next thing I want to talk about was sort of what comes next. And the way I wanted to do that was I wanted to start by thinking about what was our goal in this class to start with. What have we been doing? And you may remember on day 1, I began by saying there are basically algorithms everywhere you look in this world. You look around, everything we're doing is running based on algorithms. So Google, the internet, data centers, databases, and so on. All of this stuff is running all sorts of interesting algorithms. And we've seen a whole bunch of these type of algorithms this semester, right? We've seen things like tries that help with parsing. We've seen Bellman-Ford that helps with routing. We saw a little load balancing. We've seen B-trees, we've seen searching, we've seen sorting, and so on. So we've seen a lot of these algorithms. Okay. And so what have we been doing in 2040S so far this semester? We've been looking at all sorts of different types of algorithms. So things like, yes, stacks and queues and algorithm analysis and searching and sorting and search trees and AVL trees and B trees and hashing and graphs and all sorts of stuff. Okay. We've seen a lot about how to organize your data, something like sorting, and then how to manipulate your data, how to solve problems related to your data. The monsters are here to scare you. On the first day of class, I was trying to make sure you were properly scared. Did it work? These are slides from the first day of class. Okay, so sorry, I was addressing a question from the chat. Okay, so in general, this class has been centered around, data structures, algorithms, and how you use them for problem solving. That's what we have been doing. Okay, and we've been talking a lot, I hope, about trade-offs. So how do you choose the right algorithm for the right problem, and how do you design new algorithms for new problems? This has been, I hope, the focus of what we have done. Okay, good. So what comes next? What do we do? What can we do with this? Where do we go from here? So what I'd like to talk about for each of the topics we've covered, these are sort of 5 topics that we've covered this semester. How does what we've done relate to what is currently sort of cutting edge research or what you might see in the next class you take on algorithms? Okay, so for example, we've talked a lot about searching and sorting. We've talked about binary search, a fast way to search monotonic data. What comes next? What comes next is more general optimization problems. Binary search is a very simple example of a broad class of optimization problems. So binary search, for example, gives you a one-dimensional way of searching data. When you get on to higher dimensional data, you might use something like stochastic gradient descent if you want to search your data efficiently, okay? Or the conjugate gradient method, or so on. So in general, binary search is just the beginning of the process of how do you search data efficiently. And if you're interested in machine learning, you'll discover that stochastic gradient descent is actually the optimization algorithm at the heart of almost all the major training algorithms around. Okay. What else in terms of optimization? The other major optimization technique is linear programming. This is something you might see in CS 4234, maybe 3230. I don't know if they cover it, but in 4234, they should talk about linear programming, which is a way of solving a specific type of optimization problem, a very powerful technique for solving optimization problems. Okay. There are lots of applications, linear programming. A whole bunch of graph algorithms can be formulated as linear programming. It's a great way to find approximation algorithms. So things like, weighted set cover, multi-commodity flow, and so on. All of these can be formulated as linear programming relaxations and solved via linear programming techniques. Okay, great. And then, of course, it gets harder if you want to start solving even harder problems using integer linear programming, quadratic programming, and so on. This is a beautiful set of techniques. Okay. What else? We talked about sorting algorithms, quicksort, merge sort, heap sort. We've talked about running times, space usage, in-place algorithm, in-place versus extra space. What's next in terms of sorting? Well, first of all, we already talked a little bit about multi-pivot quicksort. This is already tells us that we are not at the end of the road for sorting. There's a lot more fascinating work on sorting to be done. For example, what do you think the fastest sorting system is out there? A few years ago, it was the Yahoo TerraSort. This was a data center, a system with 8 cores, 8 gigabytes of RAM, 2 disks on each node, 40 nodes per rack, 25 to 100 racks in total. So 16,000 cores were being used to sort. And in 2013, the Yahoo TerraSort was able to sort 100 terabytes of data in 72 minutes. That seemed pretty good at the time. Except just a little bit later, Databricks came along with 206 nodes and said, 70 odd minutes, I can do that in 23 minutes. 100 terabytes of data, I can do a petabyte of data in 234 minutes. Okay. And then I think the current record, or at least the last I checked, was the Tencent sort, which could do it in 98.8 seconds, which is utterly incredible. And my guess is this record has been broken since 2016. You can look it up and tell me what the updated record is. This is the last one I had, but I can bet it has been improved since then. Okay. Good. So it's a race. People are building these high performance parallel clusters with high performance hardware interconnects that make sorting faster and faster. It's really, really neat stuff that's happening out there. Okay. What else have we talked about this semester? Search trees. We've talked about all sorts of different types of search trees. AVL trees, B trees, skip lists, tries. We didn't talk about skip lists, did we? Cross that off the list or put it in gray. Interval trees, order statistics trees, range trees, KD trees. We've talked about all sorts of different types of trees this semester. And of course, there are more interesting things that we didn't get around to, like splay trees and red-black trees, skip lists, and so on. And these are all things that would be great. You can go and look up these others on your own. So what's next in the world of trees? There are a few big questions people are working on today. One of them is, how do you deal with high dimensional data, right? In general, we've been thinking of there being one index for our data. We have one index we're trying to sort by. What if this is high dimensional data? How do we store that? How do we index it? How do we search it? Sort of examples that people use today are things like R trees and quad trees and Z order curves and so on. But this is a hard problem, and there is a lot of work going on today. There's another question. Can we do better? Do you think that the trees we have today are the fastest possible? And it turns out the answer is not always true. We saw this with B trees, right? B trees don't inherently look like they're that much better than AVL trees, but in fact they are. It turns out that because of the way the data is stored, a B tree gets a lot better performance in practice than an AVL tree. Okay. And why is that? That's because of caches. That's because computers are not just simple flat structures. They have hierarchical memories with caches along the way, and how data is populated through these caches changes the performance. If you've taken 2100 already, you've already seen some of this. If not, you will. Anyways, and so a B tree uses the caches better than an AVL tree. Okay, right, disks are strange. Good. These are just slides on the weird and complicated architecture that you find in real machines. Okay. Good. I don't want to actually go into this right now, but it's just, I think it's fascinating how the hardware interacts with the algorithms that you're designing, and that you need to design your algorithms with some awareness of the hardware if you really want to maximize your performance. Okay. Good. And I was doing a quick calculation here about sort of how well will you do if your data is in different caches on the machine. So for example, imagine that about 2% of your data is in main memory and everything else is hanging out in cache. Well, then it turns out you're going to be spending most of your time, 300 out of 314 of your clock cycles, waiting for main memory. Okay. So in particular, 57% of your time ends up waiting for main memory, even if you have a 98% cache hit rate. Okay, so optimizing your caches is super important if you really want performance. Okay, and okay, this is with main memory. Disk is even worse. Fine. I don't know why I have too many slides here, but regardless, the point is that B trees really take advantage of this. This is why B trees work so well. This is why they're one of the most important data structures out there today, used in almost every major database, because they really optimize well for good cache performance. Okay. But of course, B trees are not the end of the story. It turns out that you can actually do better than B trees if you think about it. And you can do things like write optimized data structures where updates are even faster than B trees. This was an advertising graph from a company called Percona, but it doesn't really matter. The point was showing that to people who wanted to buy their product that you can do better than B trees. That was the whole point of this advertising picture from Percona. Okay. I don't want to talk about buffer trees, but this was just an example of how to do better than B trees. Okay, and they're right optimized data structures like log structured merge trees. If you're interested, you could look up a file system called BetterFS. which is a write-optimized file system. And in general, this is a very hot area of database research today, trying to do better than B-trees and get faster and better indexes for your disk. So the point is that B-trees may seem like an old data structure invented in the 1970s, and yet we are still seeing huge amounts of progress today. Okay, let me go on to topic 3. We talked about hash tables this semester. Okay. We talked about 2 different types of hash tables, chaining and open addressing. Okay. And we talked about how chaining has sort of order 1 expected searches and order one worst case insertions. Okay. What's happening in the world of hashing? Well, one of the pieces of new progress in the last 10 or 20 years has been cuckoo hashing. Cuckoo hashing flips around the guarantee. Whereas chaining gives you order 1 worst case insertion, cuckoo hashing gives you order 1 worst case search. Okay. And of course, what's fun about cuckoo hashing is the name, where it's named after the cuckoo bird, which goes around and pushes eggs out of other birds' nests and leaves its own eggs there. And that's kind of the way cuckoo hashing works. So again, it's sort of a fun hashing method that guarantees good search performance in a way that chaining does not. Okay. What else? You might ask questions like, how well does linear probing really work? So, linear probing, we said, can have this problem with clustering, but how well does it work in practice? And how well does it work with realistic hash functions, limited independence, tabular hashing, and so on? And there's been a whole bunch of recent research showing linear probing actually works really well, both in theory and in practice. And it's been fun seeing a revision of how we think about linear probing from the way it was taught 10 or 15 years ago. Okay. How about better hash functions? So, most of the hash functions we talk about are fairly simple, but there's been a lot of work recently on faster hash functions. What about if you're using a GPU, can we get even faster hash functions? What about cryptographic hash functions, and are they secure? Again, these are very active areas of research today. Okay. How about hash sets? So one use of a hash table is to maintain a set of items. Right? You can just use a hash table to keep track of a set of items. All I care about is, do I have this item? Is it in my set? Well, there are some very simple ways you can use hash tables to do this, such as fingerprint hash tables or Bloom filters. Okay. What else could you do with hash tables? Well, it turns out there are even better data structures out there, things like quotient filters and cuckoo filters and Bloomier filters and so on, which are fascinating next step improved hash tables that will help you to minimize space and minimize error. Okay. So again, if you're interested in hash tables, go look up quotient filters. They are a super neat extension of hash tables to solve the problem of maintaining a set of items. Okay. What else? There's been some interesting work combining machine learning with data structures like hash tables and with filters. There was this exciting paper a couple of years ago on learned Bloom filters that combined a machine learning model with a hash table, with a Bloom filter, to try to get even better performance. Okay. And so this is, I think, a really exciting area of ongoing work today that has been very much very active in the last couple of years. Okay. Okay, and this was just sort of applications of filters, keeping track of sets of things. Okay. What else is happening with hash tables? You might have heard of this thing called a blockchain. What is a blockchain? A blockchain is really just a hash chain, right? A blockchain is something that is just using hash functions to keep track of a chain of things in a secure manner. That's a very simplistic definition of a blockchain, but it's roughly what's going on. Think about Merkle trees. You saw Merkle trees in recitation. In some sense, a blockchain is just a simplified Merkle tree. Okay. Good. So this is sort of what's happening in the world of hash functions and hash tables. How about shortest paths? So what we've seen this semester is we looked at unweighted graphs, directed acyclic graphs, negative weights, positive weights, all pairs shortest path, and so on. Okay, and we saw all sorts of interesting algorithms: BFS, DFS, topological sort, Bellman-Ford, Dijkstra, Floyd, Warshall, and so on. Well, DFS is not a shortest path algorithm. Sorry, I should not have said that. Okay, we saw minimum spanning trees. We looked at prims, Kruskal's. We did not look at Beruvkas. Sorry. We did not actually end up talking about Beruvkas this semester. We talked about union find and we talked about priority queues. Okay. And in terms of what are people working on today, I think the key question in terms of graph algorithms is how do we deal with big data? How do we deal with really big graphs, graphs that consist of terabytes of data, petabytes of data? How do we solve interesting problems on super big graphs? Can we leverage parallelism? Can we leverage distributed networks? How do we deal with these really, really big graph problems? Okay. And as I hinted at, parallelism, I think, is one of the key approaches today. We've all heard of Moore's law that says the number of transistors doubles every 2 years. But we also know that more transistors no longer leads to faster computers. It used to be you added more transistors, you got faster computers. Okay, but today that is no longer true. And you can see that here. Moore's law operated well up until the mid 2000s, up until about the Pentium 4. And from about then onwards, the clock speed has not increased. Since about 2004, the clock speed has stayed about the same. Okay. So what do? It turns out we are still getting more transistors on a chip, but we are not getting faster clock speeds. And so there's been a lot of work on more and more parallelism, adding GPUs, deeper pipelines, and all sorts of clever stuff that you might have seen in 2100. Okay, good. What was I? This is just extra slides, sorry. Okay, so to make an algorithm faster, we have to take advantage of multiple cores. We have to execute lots of steps at the same time. And there's been a whole lot of work to do that, looking at multi-core, multi-socket, clusters, distributed networks, and so on. There are many different approaches to leveraging parallelism, but I think it is today at the heart of a lot of scaling when you're dealing with big data, dealing with big graphs and big data and so on. Okay. Things like MapReduce, invented by Google, is one of the key approaches today, and there are many others. Okay. Good. There's a huge amount of research today happening on sort of how to process big graphs fast in parallel. How do you find shortest paths in big graphs? How do you find properties of really big graphs? This is a huge and very active area today. Okay, good. So that's sort of my quick summary of what have we done and what is sort of the cutting edge research that's happening today in each of the areas that we've talked about. In terms of you personally, what are you going to be doing? In terms of modules, in terms of classes, many of you will next year be taking CS3230. This is the natural sort of next algorithms module and required module. We also offer a whole bunch of other interesting algorithms modules for those who like algorithms. So the competitive programming class is a great chance to write a whole bunch of code and actually implement these algorithms. Parallel and distributed algorithms, learn how to deal with parallelism and so on. Optimization algorithms focuses on optimization algorithms. Mechanism design, quantum computing, and so on. These are fascinating. This class, the name has changed, by the way. This is now called algorithms for what is it called? Algorithms for big data, big scale algorithms. I forget. The name's changed on the class. Sorry, I didn't update it on the slide. Randomized algorithms is another great area where you really see how to use randomization to build really simple algorithms to solve hard problems. Okay. Algorithms at scale is 5234. Yes, thank you. This is a class that I often teach and I can't even remember the name of it. Sorry. But yeah, this is one that I've taught a fair bit, and this is one that I occasionally teach. That's my iPad saying it's tired. What else? So in general, if you're interested in algorithms, maybe you're interested in theory in general. So we have a whole bunch of interesting theory classes out there. The basic one that you can, and my God, I got the numbers wrong on the slides all over the place. The number on this class changed. It's no longer 4,000. I think this is now a 3,000 level class. But the theory of computation class is is sort of the basic class that asks questions like, how do we decide how hard different types of problems are? Can we rank problems by different levels of hardness? Occasionally this semester we've said, oh, this problem is NP hard. That means it's hard. What does that really mean when we say a problem is NP hard? How do you show that a problem is NP hard? That's the type of stuff that we talk about in the theory of computation, and then at a more deep level in the computational complexity class. So these are great classes for really understanding what is computation, what can we do and what can't we do, okay? And then we have some classes on logic and proofs and so on, which are sort of fascinating classes to think about logic, okay? What else do we have here? Software engineering. Maybe you're most interested in building cool systems. Well, most of you will end up taking 2103, our basic software engineering class. Beyond that, we have a whole bunch of other interesting software engineering classes like the formal methods, software testing and debugging. So then 32, 16, and 17 are two excellent classes on sort of very intensive classes on system design, software development for evolving platforms, software engineering for modern application platforms. If you attend STEPS today, you'll probably see some projects from whichever of these classes is offered this semester. Okay. Yes, these are very project intensive classes. Okay. What else? If you're interested in machine learning and AI, the next class you will take is CS 2109. That's a class that focuses on a broad introduction to machine learning techniques and artificial intelligence. And then, of course, we offer a variety, in fact, many more AI and machine learning classes as well. Okay. Just please, if you go and build some AIs, please do try to make sure they don't go and subjugate the whole human race. That might not be ideal. Okay. And of course, we offer a variety of other specialized modules depending on your interests. Distributed systems, security. I didn't talk about security at all. We have a whole bunch of interesting security classes, game design, and so on. Okay. Good. The other thing I will mention quickly, at least, is one of the nice things about being at a place like NUS is there's a lot of exciting research going on here. So if you're interested in research, think about doing a UROP. That is an opportunity to spend a couple of semesters thinking about a research problem with a faculty member. Think about the Turing program. The Turing program, it's invitation only. There's no application process. But if you are involved in research, if you're doing a UROP, maybe that would be of interest. And eventually an FYP. I encourage everyone to do an FYP. It's a great chance to work with a faculty member on an interesting research problem. Okay. Okay, great. Now we are at the Archipelago's quick review quiz part of the day. I am going to open a bunch of questions on Archipelago. Here we go. So here we go. I have a quick review quiz on Archipelago to see if we've been paying attention this semester. So go over to Archipelago and tell me what you think of the answer to these questions. Archipelago is dead because that's what it does. Well, we'll give it a chance to see if it revives itself. on the screen and answer them in your head. Okay, that is, alas, all we have time for. I hope Archipelago has done its job and worked. If not, well, my apologies. We have been struggling with that all semester. One sec. I wanted to, let me see if I can find it. One sec. Where did it go? Okay, so let's go through these questions. Which of these quotes is not by a famous computer scientist? And we see number 4 here is the clear and big winner. Make things as simple as possible, but no simpler. That is the lesson of the day, and I think a good story. Okay, let's go on. Who is known for his statement, go-to statement considered harmful? Dijkstra. This is probably his most famous quote and his most famous paper, despite all the other brilliant work that he has done. Okay, what else? What algorithm was originally invented to improve Russian to English translation? That was Quicksort. When we talked about Quicksort, we recalled that this was actually invented back in the day when the Cold War was going on, and there was an exchange happening between Russian and UK universities, and they were trying to work on translation, and they invented Quicksort along the way. Okay. What problem did the most ancient known algorithm solve? We talked about this on the first day of class. That was multiplication. Okay. What else? What was the first object-oriented programming language? You have all been fighting with Java this semester, but of course, Java is far from the first object-oriented programming language. Simula 67. Simula 67 seems like it was the winner here as the most popular answer and the correct answer for the first object-oriented language. Okay. And then finally, our last quiz question of the day. In what year did Adelson, Belsky, and Landis publish their breakthrough paper on AVL trees? And shockingly, it seems like the winning answer was 1960 to 65, which I think is correct. And that tells me that some of you were dabbling on Google, since I can't imagine that many of you happen to remember those dates off the top of your head. But maybe I am just wrong here. Anyways, so it was 1962, I think was the year. 62, 63, somewhere in that range. Okay, so that was our quiz for the day. Let us get back to had to have some last Archipelago fun of the year. Okay, last thing I want to do today. People keep asking me throughout the semester, so how do you design algorithms? How do you solve algorithmic problems? And so I tried to put together my sort of 8 favorite tips for how to deal with a problem when you sit down and don't know what's going on. So number 8, try simple examples. Whenever you're stuck with a problem, find a simple example and see if you can get it to work. Of course, your example shouldn't be too simple. At least 5 items or 5 nodes in your graph. Try to avoid special cases. Running your algorithm on 1 tends not to be very interesting. Try to understand why the problem is hard when you're running this example. Okay. Number 7, naive solutions. Always start with a simple algorithm. Before you do something complicated and hard, try something simple. There are a few reasons for this. First of all, your simple solution might be good enough. Second of all, it gives you a baseline. Sometimes you develop a really fancy, complicated algorithm and discover it is worse than the simple algorithm you started with. Having that baseline, knowing what the naive solution is really important. Okay. Number 6, try special cases. You have a hard problem. You don't know how to solve it. It seems super complicated. Simplify. You don't know how to solve it in general. Maybe you can solve it on a tree. Maybe you can solve it on a planar graph. Maybe you can solve it in some simpler special case and then generalize back to the original problem you started. So again, use special cases to help you understand the contours and the structure of the problem. Okay. Number 5, make sure you know what the target is. What is the best possible solution going to look like? Is there a natural lower bound? If your goal is to do something that involves all the elements in an array, you're not going to get better than a linear time algorithm. On the other hand, if you're just trying to approximate something in the array, maybe you can do better. So you need to understand, what is the target? What is the goal? How good a solution do you think is possible? Tip number 4, think about the metrics. Think about, how do you want to measure the goodness of your solution? We talked about this towards the middle of the semester, I think, even at the beginning of the semester. How do you measure the quality of your solution? What is it you really want? Sometimes a problem is really hard because you're not looking at the right metric. And once you optimize for the thing you really want, it becomes a lot easier. Sometimes it turns out that you can't uh-oh. I see people saying that I froze. Is it back yet, or am I still gone? Hello? Is it back? Is it working again or not? Half back. Okay, let me try something else. Where did I cut out? What was the last thing people heard? We were talking about thinking about metrics, hopefully. Okay, yes, no, maybe. Hello, is it back now or not? Yes, I think it's back. Okay, good. Yeah. Okay, so I was just saying that thinking about metrics is important. Sometimes if a problem is hard to solve, it turns out that you're looking at the wrong metric. And if you optimize for what you really need, the problem becomes a lot easier. Okay, number 3, find invariance. We've talked all semester about invariance. I find invariance to be a super powerful technique for problem solving, a super powerful technique for trying to understand how and why an algorithm works. When I'm confused by an algorithm, I look for the invariance. What is always true? What does the problem require? What does the algorithm guarantee? So when you're confused, look for invariance. Okay. Number 2, try binary search. We've seen over and over this semester how binary search simplifies a lot of problems. A lot of problems turn out to have binary search hidden inside of them. So try binary search. And tip number 1, try divide and conquer. Look for subproblems, look for structure, look for optimal substructure. Try wishful thinking. If only we could solve problem X, then this whole problem would be easier. Try to find problems you can reduce your big hard problem down to smaller, simpler problems. Okay. Anyway, so these are my sort of 8 top tips for designing algorithms. So we get to the end of the semester. The goals this semester are to apply algorithmic thinking and techniques, describe the structure and operation of different data structures, assess the suitability of different data structures and algorithms, and to adapt existing data structures and algorithms to solve interesting problems. I hope that it has gone well. I hope you've learned a lot. I hope everyone has had fun and that it's been a good semester. If you ever want to chat about algorithms, please do just drop by my office or Zoom or however we're meeting in these days of COVID. I would love to meet you all in person at some point in the future. I hope to see you all around NUS in the future. And so congratulations, that's the end, it's over. And I will see you all at the final exam. Thank you.
Hi, Prof. How do I visit your office?
Yeah.
How do I visit your office?
Well, during normal times, I usually am around my office on the third floor of Com2 a fair bit. The last couple of years, not so much. So alas, these days it's harder to drop by, but hopefully in the future we'll go back to more normal times, and in which case, yes, feel free to drop by or send me an email. We can set up a time to chat.
Kind of failing in the recent chapters.
Yeah, no, I'm always happy to chat.
Yeah. Like, I don't know how, I mean, for the last week's part, like when you mentioned that for the table, you can reuse it to KE. You mentioned something along the lines of like how like with the table and memorization, you can reduce the V square into a 2E a level. And you elaborate.
Yeah, right. So the point here was that instead of analyzing each subproblem individually, you could look at what is the total cost of solving all the subproblems in a row.
Yeah, but like, how is that equivalent to 2E?
So I think we decided it was E, not 2E. I think I said 2 incorrectly. But I think it was E because we observed that to solve all the subproblems in a row, we basically have to look at each edge exactly once. That if you look at sort of the work that you're doing to solve the subproblems, the work that you're doing to solve the subproblems is essentially exploring edges in the graph. And you look at each edge exactly once, and therefore the cost is E.
You look at each edge exactly once.
Yeah, if you looked at what happens when you solve all the problems in a row, right? The way you solve the subproblems in the row are you look at a collection of other subproblems and you take a max or min or whatever over those subproblems.
So because for each row you have to find the weight of the edge connecting the one edge to another for all vertices once, so it's called E. Okay.
Yeah, exactly. Basically, for each subproblem, you're looking at the neighbors of that node. And if you just look at, well, all the neighbors, that's going to be all the edges.
All right, okay. That solves the problem.
Good.
Thanks.
Good. Cool. Well, as I said, everyone have a good rest of your week, a good reading week, and I will see you all at the final exam. If we don't secure Orbital, are there other programs? So Orbital is a great program, and I hope that many of you can do it. Beyond that, I don't know. There's CVWO, but that's also pretty hard to get a slot in. And then there's this interview program that I just mentioned, which also could be useful. So yeah. Am I doing ES2660? No, I'm not teaching ES2660. No, I'm not running the interview program. In fact, I think a lot of it's going to be done by alumni and people who've actually gone through this interview process more recently. Signups for CS2040S tutors will happen, well, for next year. The next time I'm teaching it, it'll happen at the end of next semester. For next semester, there's also a version of 24DS taught by someone else, and that will probably happen sometime over the summer. But in terms of tutoring a year from now with me, that, be in touch in the end of next semester. How good do tutors have to be? Well, you've seen what your tutors do, and you've seen how hard it is. That hopefully gives you some sense. To be a tutor, you have to have both a solid understanding of the material, and you also have to be good at explaining it, answering questions, dealing with questions where you don't know the answer, because we all get questions we don't know the answers to, and more. So it is both knowing the material part of things, as well as a teaching and communication skill set. Okay. Yeah. Okay. I'm going to go, but I will see you all around.